Our last exercise demonstrates soldering a flat pack or planar mounted component. This one requires all the skill and sense of timing you've developed in the earlier exercises. You'll be using the small iron tip, the 1/16 inch diameter one, and the small sized solder, 1/100 of an inch in diameter. The leads are small and delicate, so you'll use what's known as a reflow technique, putting the solder on the pad first and then reflowing the solder while holding the lead in place on top of it. Let's watch how it's done. The first task is tinning the pads. Notice the placement of the solder and the direction in which the iron wipes. After all the pads have been tinned, the area is wiped with solvent. The bending is done with a lead forming tool or a pair of duck-billed pliers. The leads may need to be trimmed for a proper fit. In some circumstances, the specifications may require pre-tinning of any gold-plated leads. Pre-tinning will prove the solderability of the surfaces and will minimize the gold solder contamination. When pre-tinning is not required, leads are first cleaned with solvent. For reflow soldering like this, where no additional solder will be used, new flux must be put on separately. Then a piece of tape is used to temporarily hold the component while soldering. The component is positioned so that each lead is centered over its pad and extends almost to the end of the pad. The procedure is to first solder the leads at opposite corners. Then the other leads are soldered, skipping around to prevent heat from building up. Here, a pair of tweezers are being used to provide a light, downward, positive pressure at the upper lead surface. The workpiece indicator is the flow of the solder from the pad up onto the surface of the lead. When the flow is observed, then the iron is removed while maintaining downward pressure until the solder solidifies. After soldering, all traces of flux are removed from the leads with solvent, and the result looks like this. Here are the characteristics of a preferred joint. Notice how each lead is straight, parallel to the pad, and centered on it. Solder has completely wet the full joint. There's unbroken solder coverage over the top of the lead and a continuous fillet along the sides, end, and heel of the lead where it meets the pad. At the heel of the lead, note the height of the fillet. It should be at least 1/3 the total distance between the pad and the horizontal part of the lead. The angle here between the lead and the pad is also important. It should be 60 degrees. Here are a number of unacceptable joints. The leads are not centered and they overhang the edge of the pads. Doing reflow soldering like this takes considerable practice to do perfectly. It's difficult because there's no direct clamping of the lead during soldering, and the lead tends to roll up. You can easily solve the problem, however, if you have one of these available. A lap flow tool, designed especially to make this type of joint. Like the thermal wire stripper we saw earlier, the lap flow tool is plugged into a power supply and its heating is controlled by the foot switch. In use, the tip is placed on the lead and the foot switch depressed to instantly heat the tip. When the solder flows, the tip is slid towards the middle of the lead and the foot switch released. Then for a moment, the tip is held motionless with light pressure on the lead until the solder has cooled. The tip can then be removed without disturbing the joint. The big advantage of the lap flow tool is that the tip holds the lead clamped in position throughout the whole operation. It's put on cold to clamp the lead down before soldering, and then holds there during both heating and cooling. You've now seen all the basic techniques for high reliability soldering. The procedures shown are new build soldering on boards that have never been worked on before. This type of soldering is different from the more difficult soldering encountered in repair work. In repair, some new considerations come in. Often, coatings and bad components must be removed first from the joints, and in many cases, the joints are very difficult to get to. Sometimes they're completely buried under a number of other components that must be removed first. Also, there is usually much greater mass at these joints because of the number of leads terminating there. You have to overdrive these masses with sufficient heat to melt the solder, without at the same time damaging either components or board. These problems are covered in other courses that are available in this series. The next one covers component removal, explaining the limitations of some of the currently used methods and the advantages of power desoldering with continuous vacuum. This method makes possible the non-destructive removal of any type of component.